Welcome to part 2 of our introduction to buffer overflows. So far, we've seen how buffer overflows work in principle using a stylized processor and a somewhat simplified explanation. Now, we're going to make it real. That is to say, we're going to discuss the processor and the addresses as they are really used in a modern x86 machine. And we'll also show little bits of the assembly that is relevant for this particular exercise. But let's start with the memory layout of a Unix process. So we're basing this on Linux, and this is a 32-bit Linux process where the stack, the green part here, represents a stack, contains a number of things. It starts with address B and then all Fs. It's a hexadecimal number. We'll talk about that in a little while. It starts with the environment and argument strings and some environment and argument pointers, followed by the stack as we discussed it in the introduction to memory to buffer overflows. Okay, so this part is what we've basically seen before. But like I said, above the normal stack with the return addresses and the local variables and so on, we have the environment variables and some pointers to the environment variables. Okay. Below the stack, we find other bits and pieces. All the way at the bottom of the memory, we find the text segment. Text is another word of saying code. This is where the instructions live. Instructions live there. Okay. Above that, we have the initialized and uninitialized data segment. Uninitialized data is also referred to as the BSS segment. And above that, we have what we refer to as heap memory. This is the memory that you will actually get a piece of when you call a function like malloc. Okay. So we have text, data, BSS, heap, and then the stack. Okay. The memory above this is not accessible. Okay, this is where the kernel is mapped. Right then. So when we're talking about the memory, as we saw on the previous slide, we write the addresses in hexadecimal. Okay. For instance, if we disassemble the code for the function IE that we discussed in the first part of this series, if we disassemble that, we will actually see addresses like these. Okay, starts with OX to indicate that it's hexadecimal, and then some number. Okay, hexadecimal is not very complicated. It's a little bit different from decimal. They count in base 16 rather than base 10 as in decimal. So we basically have, because we can't have more numbers, we only have numbers from 0 to 9, we use the remaining ones of the 16 in letters, right? So we have 0, 1, 2, 3 to 9, and then A, B, C, D, E, F, and I see there's a 9 missing there. A, B, C, D, E, F. A represents 10, B 11, C 12, and so on. Okay, so FF would be, well, counting in base 16. So we take the second character, which is F, which is a 15, times 16 plus the second character, which is F, which is 16 to the power 0, which is just 15. So this is 16 times 15 plus 15 equals 255. Okay. Likewise, AE is 16 times the value of A, which is 10, plus 14, which is the value of E, is 174, and so on. So what's convenient about this is that you can use exactly 2 characters to denote the value of 1 byte. Okay, so for instance, AA, BB, CC, and DD is a 4-byte value. Okay. So that allows us to, for instance, translate this address here to a decimal value. Okay. So we basically we start from the right, so 0x 08 04 8431 equals 2 to the power 0 times 1, okay, plus 2 to the power 4, 16 times 3, plus 2 to the power 8 times 4, plus 2 to the power 12 times 8, plus 2 to the power 16 times 4, plus 2 to the power 20 times 0, plus 2 to the power 14 times 8, and 2 to the power 28 times 0. Okay. If you add them all up, you'll get the decimal address. Okay. What else do we see? So now we know what these addresses mean, how we calculate them. What else do we see? Well, we see a number of things. We see a number of instructions, and we see that some instructions are just 1 byte. For instance, going from this instruction to that instruction increases the address by only 1, so that's a 1 byte instruction. But other instructions are a little bit longer, okay? So they increase the address by more than 1 byte. In this particular case, 2. So we notice that the x86 has a variable sized instruction set. Some instructions are 1 byte, some 2, some 3, and so on. In fact, the x86 has a horribly complicated instruction set with very little regularity. Okay, so there's that. What else do we see? This is the start of a function. Okay, so this is a very typical prologue of the function. Okay, a push of EBP and a move of ESP to EBP. What does that mean? Well, the EBP register is what is known as the frame pointer. Intel refers to that as the extended base pointer. Okay, so what's happening here is that right after this function is called, right, and the return address has been put on the stack, return address is there, we now push the current value of the base pointer on the stack. So that means this will be the old base pointer, old frame pointer as we refer to it in the first part of this lecture series. Okay, so this is a push of EBP, pushing the old frame pointer. Okay, and a move of ESP into EBP basically means that we pushed it here, so ESP is pointing here. The value of ESP will now be the value of EBP. Okay, so it will be stored in EBP. So the frame pointer is now pointing to this location, which is what we also saw in the first part of the lecture, but now we see how it's actually done. It's done by this move. All right, let's now look at the call, because this only works, of course, if the return address is also pushed onto the stack. Well, that's done in the call. So here we see a call instruction that calls this address, right, which happens to be the get URL function, as expected, which exactly coincides with what we've seen in the first part of the lecture. Finally, we see a return which returns from this function. So it pops the return address of the stack and returns to that address. Okay, now that's preceded by a pop instruction. So the pop instruction first removes the old frame pointer from the stack and places that in the frame pointer register. So the frame pointer register will now be pointing to the basically the start of the previous stack frame, and then ESP will be pointing here, and at that point we return and remove, which automatically pops this address of the stack and moves the stack pointer here, and the program counter will now be executing the code that's at that return address. So this actually coincides exactly with what we've seen so far. Okay. So again, EBP is the frame pointer which we push onto the stack. Okay. The frame pointer is a register. Now we place the frame pointer on the stack. So this is now the old frame pointer, because what we do next is store into this frame pointer, into the frame pointer register, the current value of the stack pointer, which is exactly the pointing to the place where we pushed the old frame pointer. Now we do the call, and the call automatically pushes the return address onto the stack. That is the address of the next instruction to execute after this function returns. Okay. Then we do a pop of EBP, which means pop of the frame pointer. So we read one value of the stack and move the stack pointer up, and then store that value into the EBP register, into the frame pointer register. Okay. And finally, we return, which pops the return address of the stack and jumps to that. So that was one function. We might as well have a look at the other function also, get URL. It was a little bit more complicated because more stuff was happening, i.e. only called get URL, didn't do anything other than that. Get URL did a bunch of things. It declared space for a buffer, it read from the keyboard, and some other things. Right. So let's have a look, but we don't necessarily want to understand everything. Okay? Just a basic understanding will do. Again, we have here the start of the function, okay, and we see here at the end of this function we return. Moreover, we see that there is the exact same prologue to this function. So the prologue of all these functions look exactly the same. We push the old frame, the frame pointer, so that becomes the old frame pointer, and then we move the current value of the stack pointer into the frame pointer or the base pointer register. Okay. It's the exact same prologue. What we see here is a subtraction. So we subtract the hexadecimal value 18 from the ESP, the current value of ESP. So if ESP is currently pointing here, the place where we just stored the old frame pointer, we will now subtract hex 18 from that value and make it point here. Okay. So what does that do? What is hex 18? Well, remember we had to multiply this 1 by 16, so it's 16 plus 8 equals 24. So it reserves 24 bytes on the stack. Okay. Why 24? That's odd. Didn't we say that the number of bytes that we wanted in the buffer was 10? Okay. Yes, that's right. So we have 10 bytes in our buffer, but we also remember that we had 3 parameters to the function read. So read actually took 3 parameters. Okay, so we have 10 bytes plus 3 parameters, and all those 3 parameters happen to be 4 bytes each. So together that would be 22 bytes, 10 plus 3 times 4. And then there is 2 bytes because we want to make this nice 4-byte alignment on the stack. Okay, so that's what's happening there. We're reserving space for the buffer and for the 3 parameters to the read function. Finally, we see a bunch of things which we don't necessarily want to understand at this point. Has some things to do with the parameters. And finally, we see a call to the read function. Okay, so here's a call to read, and then when we're done with the read, we leave the function, which is basically popping EBX of the stack and returning. Okay. So we currently have these two functions, IE and getURL. Okay? They are in memory, which is shown on the right. This is the code memory. We have getURL here, we have IE here, and we have the read function here, just like before. It's just a little bit more realistic. We've changed the code a little bit. So here we see that we've made the buffer slightly larger than 10 bytes. 10 bytes would be ridiculously small. We've made it now 40 bytes. And we're reading from the keyboard, but that, if you're using the C programming language, basically means you're reading from STUDIN, standard input. Okay, so we're reading from the keyboard. The other thing that we see is that the functions IE and getURL have been swapped in memory, right? So in our previous representation, we had IE at the bottom and getURL above that. Well, it just so happens that the system put them at a different order. So the addresses of getURL are lower than the addresses of IE. We have all the instructions there. So if we look at the IE instructions, we start with the push EBP, then we move to the saving the stack pointer into the base pointer register or the frame pointer register, calling the function getURL, popping the frame pointer or the extended base pointer of the stack, so we actually have base pointer pointing to the previous stack frame, and returning, which pops a value of the stack and uses that as the next instruction to execute. So we see exactly what we've discussed before. Okay. So what happens to the stack? This was the part, basically the code. What happens to the stack? Well, the stack looks exactly as before, except that we now have average stack entry being 4 bytes. So it's a 32-bit machine, so every stack entry is a 32-bit value. But other than that, it's exactly the same. So we have here the 10 bytes that we saw earlier. Okay. We have an old frame pointer. We have, sorry, this is not 10 bytes now, this is 40 bytes. We have an old frame pointer. We have a return address. We have the 3 parameters over here. Everything is exactly the same. Maybe the addresses look a little bit differently because they are now hexadecimal, but other than that, nothing has changed. Okay. And the exploit, therefore, is also exactly the same. All we need to do is overflow these 40 bytes. Okay. Change the return address to make it point to, for instance, the first byte in the buffer. And if we have our instructions stored at this area, we can now execute our own instructions. We've diverted the flow of control for this program to our own instructions. So that's really the long and short of a simple buffer overflow, simple stack smashing attack as it's also called. Okay. As long as we stick our program in this buffer, we can execute whatever we want. So we've taken over the program. Okay. Sometimes we don't even need to change the return address or indeed execute any of our code. Okay. Because sometimes it's sufficiently interesting to overflow, to overwrite some variable. Here's an example. Okay. The program is really simple. It has a small part of logic which basically reads from the network. Oh, it actually does an authorization check first. Okay. And if you're an outsider, you will not have the proper authorization to show the privacy sensitive medical information. So there's an authorization check, and then the program reads from the network the name of maybe the patient information that the patient that you want to see the medical information for. And then if you were authorized, it will show you that medical info, and if not, it will tell you that you cannot see the info. Okay, so what could possibly go wrong here? Well, we're reading from the network into this name buffer, and the name buffer is only 10 bytes long. Okay, so and above the name buffer on the stack, we find another variable. So this particular case, the get medical info function has two local variables. An authorized variable, which is a boolean, which is initialized to false, and a name variable, which is a buffer of 10 bytes. So if we're reading from the network into the name buffer and there's no proper bounds checking, it means we can overflow the name buffer, and overwrite the authorization variable that is over there and set it to true. In C, anything that is not 0 will be interpreted as true. So as long as we change that value, the authorized value, to 1 or some other value, it means that the authorization is now set to true. And that means we will pass this test and get to see the sensitive medical information. Now, the other thing that we can do is target other addresses. So far, we have basically used the stack as both the place where we overwrite the return address and also where we store our code. So we have basically set the return address to return to something that is on the stack. Okay. This may sometimes be hard because perhaps you don't know the address of whatever is on the stack. Okay. So actually getting the address right might be hard. But you can also target other locations. For instance, if you control the execution of the program, so if you actually can type in the command to execute this program, you also control the environment variables of this program. Okay, so you can actually place your code, your malicious code, in such an environment variable, and then jump there. Okay, and there, at least in somewhat older systems, the addresses will be well known because you know where the stack starts, where the environment variables start. So you can actually target that. Okay. Still, the attacker only needs to stick a program in the buffer or in the environment, and away he goes. Now, the question is, what does such code look like? We're now talking about the attack vector. We understand the basics of the buffer overflow. This is how it works. Fine. We understand the addresses. Fine. Now, what does such attack code really look like? Okay. Well, such attack code is sometimes referred to as shellcode, and it's packed in an attack vector. Okay. The attack vector typically consists of a so-called nopslat, the actual shellcode, which is the functional part, and the address of the shellcode. Okay. Clearly, the address of the shellcode is what you want to have in your return address. So this will have to go into your return address. This is the stuff that you want to execute, and this is, well, a bit of NOP code, no operation code. So the shellcode address is the address of the memory region that contains the shellcode. The shellcode itself is the sequence of machine instructions. Typically, perhaps you want to execute a shell, that's why it's called shellcode. And the nopslat is a sequence of no operations. Okay? And why do we have that? Well, it means that we don't necessarily have to get the address where we want to jump to exactly right. Okay? Getting it right might be hard, right? Perhaps you don't know exactly what the address is at which your buffer begins. Right? But that's okay as long as you get it right within, an approximation. If you get somewhere in the nopslat, that will just start executing no operations, no operations, no operations, no operations, no operations, until it arrives at the shellcode. Okay? It will eventually reach the shellcode. Alright then, so now we have this attack vector that consists of a nopslat, shellcode, and the address of shellcode. How do we create that? Well, first we're going to have to create the shellcode itself, the blue bit in the middle. Okay, and the shellcode is nothing other than a little bit of assembly. Okay, this is a particular bit of shellcode which will do an exact VE, so it will actually try to execute some program And we're not going to go into all of this, but you can see it's just another bit of assembly that not unlike what we've seen before. And you can kind of see that it's doing, it will try to execute a shell, bin/sh shell. But how it does that is kind of not so important at this point. Okay, so we've written this little bit of assembly in this sort of symbolic assembly language, and we translate that using an assembler to the actual binary representation. So just machine instructions if you want. Okay, that will be our shellcode. You can kind of see that it is equivalent. Here's the /bin/sh followed by some characters. It's still in there. So that's the actual shellcode. That should be part of our attack vector. Now, the next thing we want to do is prepend the nopslat. So the nopslat is just a bunch of no operations. And that's hexadecimal 90 is a nop operation. Okay, so that's what we just create a whole bunch of those, and that's our nopslat. We add our shellcode to that, and finally we attach the address. So in this particular case, it was this address which was attached to that, and then we have a complete attack vector. Now, in reality, this is really what the shellcode frequently looks like, but things are a little bit more complicated, because very often the shellcode will not just be ready, the actual real shellcode that the attacker wants to execute, but rather it will often be packed. So it will often be encoded in a clever way. So the shellcode consists, if you look at it, of a small routine that is called an unpacker. Okay, and then some encoded shellcode instructions, like it's like encryption, right? So you have an unencryptor and an encrypted part, and you first need to unencrypt it. It's not always done for encryption, but this is how you could think of it. Okay, so and what the unpacker will do is it will read the encoded shellcode and then write the actual shellcode that it wants to execute. So it's like an encryption routine. It reads the encrypted data and writes the decrypted data, so that eventually it produces the actual shellcode that the attacker wants to execute. Okay, so there's an encoding. All that you need to remember of this, and that is that there is some encoding in place. Okay. Now, why do you think encoding is so frequently used? Well, one reason might be that your shellcode shouldn't be very easy to spot, right? So it shouldn't be something, if you know exactly the instruction sequence, you could just have a filter in your network scanning for those instruction sequences, and if you encounter them, then say, okay, I know what this is. This is shellcode. I don't want to allow this. Okay. So to do that, maybe you can pack it differently every single time. So if you frequently change the packing, it's going to be harder to have a signature that detects this attack vector. Okay, this could be one reason, but one perhaps even more important reason to use some form of decoding of encoding is that functions like string copy will copy data into a buffer. Now think about that. It will copy data until it encounters a null character. A null character terminates a string in the C and C++ languages. So what happens if your shellcode also contains a null character? Okay? In other words, if your shellcode contains a null, we have a problem, because the shellcode will not be copied using string copy. Okay? It will copy it until the string copy encounters that null character. After that, it's game over. Okay, so what we need to do as an attacker is make sure that our shellcode does not contain such a null character. Okay, so we just maybe make it a 1 character, and then dynamically when we start executing, decrement it by 1, and it becomes a null. So we dynamically generate the nulls that we need because we cannot have them in our shellcode as we deliver it to the program, as we deliver it to functions like string. So we need to patch our shellcode dynamically. And then patching is kind of another way of doing unpacking, right? So we're unpacking it by adding the zeros, the nulls that we need. Okay. So now we basically reached the end of part 2. We should understand buffer overflows, and let's see if we really do. Okay. So here's a program, a really simple echo server. What the program will do is it will welcome clients that connect to it and echo what they send on a socket, on a network connection. Okay, so forever it tries to echo whatever clients may provide to it, and add to that a welcome string. So while one means it will do things forever, and what will it do forever? Well, it will call the echo function forever. Okay, and echo does nothing other than copy a global welcome string, which is gwelcome, and it says welcome to our system, into a buffer called reply. Okay? And the length is determined by string length. Okay, so it's copied the gwelcome string into the reply buffer, and then it writes to the socket, so it writes to the client that connects to our server, type your name. So the client types its name, and that name is then copied also to the reply string. So it becomes welcome to our system and then our name. Okay. And that will be written back into the socket. So without the comments, it looks like this. It's a little easier to read. We copy the gwelcome string into our reply buffer, and then we read into our name buffer and copy whatever we've received from the client into the reply buffer at an offset length. So again, here's our reply buffer. We first wrote the welcome string, which is welcome to our system, which has a certain length. And then at the next part, we write the name. Okay? And that's therefore reply plus length. Alright, so once we have done that, we have a complete answer, and that's what we're going to write to our client. Now the question is, can we exploit this program? And I want to leave you with that as a challenge. In the next part, the third and final module of this series, we'll actually look at more advanced exploitation to get around certain countermeasures. So we'll look at countermeasures and at ways of evading those countermeasures. For now, we would like you to just have an idea of how to exploit a simple C programming a program like this one.